Okay, so the title of my talk will be how we adopted Apache Pulsar after a long evaluation on multiple dimensions. So I will take you through the journey of how we did the evaluation on multiple angles before we adopted it. Uh, so this is me. I've been the Senior Director of Engineering at Splunk after our stream acquisition. Before that, as Alexi pointed out, I have been involved in streaming systems for quite a while in terms of developing Heron and developing Pulsar. Um, so these are forward legal-looking statements regarding Splunk. So the title of my talk will be as follows. First, I'll give an intro to Splunk. Then, based on whatever the applications and other things that we see, I will outline some of the streaming system requirements, and we'll go through how Pulsar satisfies those requirements. And then I will outline a couple of slides on how we use Pulsar at Splunk, and I will take questions. So just to give an idea about what Splunk is what we call as a data to everything platform, where we are primarily focused on IT, security, DevOps, and business process, where we collect all the data and process it and get real time and get insights that is used for security, compliance, and other various several use cases that how you engage with data. And we have a powerful Splunk application that can drive some nifty dashboards. So, so when we are at Splunk, we saw a lot of emerging use cases that includes several applications. One is real-time monitoring and notifications. And the second one is interactive applications, where you get the log from interactive applications, decide what feature to keep it on and what feature to turn it off. So based on certain regions and other things. Then log processing and analytics, more in real time. Then IoT related analytics, where the data is coming through certain manufacturing floor or factory floor, and but you want to get closer to the source rather than getting the data first into a system, then post-processing. Instead, you wanted to get the data insights in the stream itself. And then from a broader perspective, there are a bunch of ETL, data that is produced by several myriad of devices and sensor needs to be cleaned up before gets into the appropriate insight mechanism, then gets into the data at rest. So though, as a part of that, streaming ETL is a big use case. And of course, we want to have real-time insights or visibility as the data is coming through. So that is a whole slew of analytics that you can do on the fly. And as the data is generated and streamed through, we might want to route the data into multiple different destinations depending upon the value that it provides, whether it's a high value or low value. Depending upon those things, we might want to route to different destinations. And finally, there are applications which require some kind of event-driven flows, like in the case of microservices, where one event is subjected to several steps in the processing before we reaches it requires a response. So in those kind of situations, we need a messaging and streaming systems. So there are several dimensions that we evaluated a streaming system that includes scalability, how fast we can scale and how soon we can scale it down. Durability, what are the different type of durabilities that we based on the application requirements, and how fault tolerant the system is, and how available the system is. Then whether when we have multiple teams and multiple tenants and customers are sharing the resources, how to isolate them when needed, and what type of client languages that to interact with, and what type of messaging models like streaming versus queuing, and what type of persistence it provides. Then how to ensure type safety in the clients, and everything that you write into the system can be enforced, and how easy to deploy in the Kubernetes, and how to operate the system and what are the disaster recovery scenarios in the case of one zonal failure as well as in the region, the entire region failure. What is the total cost of ownership, and how do you observe the system for operability reasons, and because of the open source nature of the components, how it's the ecosystem or what the kind of adoption it has, and what kind of community, then what is the licensing model. So there's a bunch of dimensions that we need to evaluate. So let me go through each one of them as soon as possible. So the first is scalability, and traffic can widely vary while the system in production, at least in Splunk, and the system needs to scale up with no effect to publish and consume throughput and latency. And then we need to support for a linear increase and decrease in throughput as new component or new nodes are added. And when the system is stressed out as the new machines are added, the load should be spread out automatically rather than doing manual intervention at any given time. And the scalability should be across multiple dimensions, both serving and storage. So this is possible in Pulsar because of the fact of the multi-layered architecture. As we see, there are three layers of architecture. One is the compute layer, which consists of the workers layer, where it manipulates the data within Pulsar. The second layer is the messaging layer, where you publish data into the messaging layer and consume data out of the messaging layer. And that is where the broker layer is. That can be scaled separately. Similarly, the storage layer, which provides a persistent for the serving layer when the data is spilled over to disk. So that is a bookie layer, and that bookie layer will be able to store the data and retrieve data as and when needed, and that can be scaled depending upon whether disk is full or the disk or scaled down depending upon the layers. So scaling down because of storage needs. So essentially, it's independent layers for processing, serving, and storage. Then messaging and processing are built on top of Pulsar, whereas the storage is built on top of Apache Bookkeeper. And this all comes in a single package for Apache Pulsar. So durability. Splunk has applications with a different type of durability requirements. One is persistent durability. So in the case of, in this case, no data loss is accepted even in the presence of node failures or even entire cluster failure. And this is useful for applications like security and compliance, where we don't want to lose any data that captures one intrusion or a blip in the data, a needle in the data. Whereas the replicated durability, it says no data loss in the presence of limited node failures, because by just viewing by replication, if you have a 3-node replication, you can survive up to 2-node failures, right? And this kind of replicated durability is good for collecting machine logs and processing them on the fly. And transient durability. So in the sense like, I don't need durability at all. As long as the system is up, I'm fine with the durability guarantees. So data loss in the presence of failure, especially in the case of metrics data, and which are just showing more of a trend. So even if you lose the trend, that trend will reoccur. They're reproducible because of the fact that the CPU usage has increased, that trend will continue to be there. So in this case, some data loss is acceptable. So Pulsar, based in its architecture, provides different type of durability. So how does it provide? So when the data is ingested from a producer and it goes into broker, then from broker, it goes into the bookie. And when the data is received in the bookie, the data is f-synced. So m-synced and flushed into the disk before the acknowledge is generated from the bookie. So from that point of view, it gives you a persistent durability. So now brokers can at any given time or can replicate the data across bookies. So in other words, whenever you send a message that is given by producer to the broker can simultaneously replicate the data into bookies. So then all the bookies will do the f-sync and give the acknowledgement. Once you collect all the acknowledgement, only then you can give the acknowledgement back to the producer. So by the time the data gets into the producer, by the time acknowledgement gets into the producer, you not only f-sync the data, but you also replicated the data. Because of the f-sync and the replication, we can satisfy both the persistent and replicated durability. Now, if you wanted to turn on f-sync for replicated durability, you can do that as well. So then the third one where transient durability. So that does not involve the bookies. Instead, the data comes from the producer, goes to the broker, and broker acknowledges, and it caches in the broker. Now, when the broker goes down, you incur a data loss, but that's only for transient purposes. So essentially, three different forms of durability is available. So the third one, the ability of the system to handle fault tolerance under different component failures. Ideally, it should be without any manual intervention to a certain degree. So Pulsar can tolerate the broker failures as well as bookie failures. When the broker failures occur, the topics that are served from the broker is shifted into the other broker, and the system continues to serve data, not only from a published point of view, but also from consumed point of view. No copying of data, nothing of that sort. So which means brokers are essentially stateless, and you can scale up and scale down brokers. You can tolerate failures of brokers. Similarly, like when you have a bookie failure, the system writes will shift it to the new set of nodes. So for example, in this case, when the broker 2 failed, the writes will shift to the other 1, 3, and 4 broker, and the background process copies the data so that we can keep the replica factor up actually. So now, because of the fact that the Pulsar is divides a particular data into smaller segment, or particular partition into smaller segment, at any given time, the data will be running on any 3 nodes, assuming a replica factor of 3. If one of the node in the replica goes down, then the current segment will be closed, a new segment will open on a new set of bookies. So because of that capabilities of the segment architecture, the write availability of the system is very high, in the sense like as long as any 3 bookie nodes are available, or 3 storage nodes are available for a replica factor of 3, it will continue to keep writing that data, so without losing it. So high availability. So system should function, continue to function in the cloud or on-prem, and the following conditions if applicable: when 2 nodes or instances fail, or when availability zone or rack fail. Now we saw some of the broker failures and bookie failures. Now let us look at the deployment in the cloud, where you can have zone failures. So bookies provide us some kind of rack awareness. For using rack awareness concept, we can bring up some nodes in zone A, some nodes in zone B, some nodes in zone C, and when the broker sends the replicas to replicate to the bookies, it will send to one bookie on each zone. So that way, what happens is when the segment, when the particular zone goes down, not only does the segments become unaccessible on that zone A nodes, the reads and writes will shift it into the other zone B and zone C. So that way, like, we can survive zonal failures very easily. In the presence of zone and rack failures, data is available in other zones. Sharing and isolation. Systems should have the capabilities to share many applications on the same cluster from cost and manageability purposes, and isolate different applications on their own machines in the same cluster when needed. So this comes into the concept of multi-tenancy, which is inbuilt into Pulsar, where each cluster has the notion of several tenants, and each tenant can have the notion of namespaces, and within each namespaces, you can have multiple topics. So those, in addition to that, you can control storage quotas at a particular tenant level, how much flow control, back pressure, rate limiting, those kind of features are already available in Pulsar that we can control. We can isolate a particular tenant in this, based on software, and if need comes, we can move the tenant to a particular set of nodes or hardware elements, So then where you can constrain some tenants on a subset of brokers and bookies. So these are all the quota enforcements. So requirement number 6, which are the client languages. In this case, how many languages we support? Currently we support like 5. We added the Node.js support, which are officially supported by the project. In addition to that, there are a few languages, .NET, then Scala, then Rust support is provided by the community themselves. But officially we support 6 languages by the project itself, open source project. So then requirement 7, multiple messaging models. I mean, some applications require collect once and deliver once capability, which is like an example is process the S3 file that is queued into the messaging system and ingest into Splunk index, and receive data once and deliver it multiple times, which is essentially like multiple pipelines coming in and share the same data for different type of processing. And for these kind of this thing, we don't want to use multiple systems from a cost and operations perspective. And then we don't want to emulate one system on top of the other, because then we have to write a lot of emulation code that requires maintenance. So luckily, Pulsar provides both the messaging models. From a messaging point of view, it provides exclusive subscription and failover subscription. From a queuing perspective, it provides shared subscription and the key shared subscription. And since it's providing native support for both the different models, you don't need any extra code for infrastructure level that require maintenance. So the streaming model or the messaging model, you have the exclusive subscription. At any given point, one consumer will be consuming the data, and if any other consumer tries to connect, then it will get an error. And also the data will be delivered in order. And by creating multiple subscription for different type of different subscription for different consumer, you can consume the same data multiple times. So then failover, in case if the consumer fails, you want a standby consumer to consume the data, yes, you can do a failover subscription. Again, the data will be served in order. When the consumer 1 dies, consumer 2 will be delivered the data with where the consumer 1 left off, based on the cumulative acknowledgement that we received on the subscription. And subscription maintains a state, everything within Pulsar DB. The clients no need to maintain any kind of a state. Pulsar tracks kind of everything. So on the other hand, in the queuing models, the data is round robin to the consumers. So in other words, it's each of the data will be given to, part of the data will be given to consumers, each of the Consumer 1 gets M2 and M4, while consumer 2 gets M1, and consumer 3 gets M0 and M3. And so this is for the queuing model. So because of that, this is again a variant of the shared subscription, which allows you to do route by based on keys to a particular consumer. So the key difference between the two is selective acknowledgement versus queuing versus cumulative acknowledgement. And the selective acknowledgement, every message is acknowledged and kept track, and that is we used for the queuing model, because each consumer can be going at a different pace. And on the other hand, the failover subscription and the exclusive subscription, we do a cumulative acknowledgement. The last acknowledged message is an indication that the client has subsumed or consumed the messages that has come before. And the queuing side, we can track millions and millions of acknowledgements. That allows the system to scale. So the persistence, offload the colder data to lower cost storage, and it could be either manual or it could be automatic with a configurable threshold, and it should be transparent to publishers and consumers, allows for nearly infinite storage at low cost, compliant and security. So this allows, this is needed especially for events where secure as kind of this type applications where you wanted to do event sourcing and where you want to replay the data from some period of time, and look for some patterns. So type safety. Splunk applications are varied. One class requires fixed schema. The other class requires fixed schema with evolution in mind. And then the third class requires flexibility for no schema or handle at the application level. So we don't want to bring yet another system for schema management and support for different types of schema type itself. So Pulsar provides an inbuilt schema registry that provides type safety to applications, and its server side system enforces type safety and ensures that producers and consumers remain synced with respect to schema. Schema registry also allows clients to upload on a topic basis, and schemas dictate what type of data types are recognized or as valid for that topic. So requirement 10, ease of deployment in Kubernetes. Kubernetes is a popular orchestrated at the deployment environment, and we should be able to easily deploy in Kubernetes. And the surface area that gets exposed outside Kubernetes should be minimal. Then segregation of some of the nodes receiving the data from external clients and cloud-like environment should be possible as well. And should be able to deploy CI/CD pipelines for testing and deployment as well. So the key thing is we have a notion of a Pulsar proxy, which allows you to have only one endpoint exposed on the Pulsar side of things in front of an ALB, and that allows you to spray the traffic on the Pulsar proxy, which in turn directs to the appropriate broker, which is serving the topic. So because of the way the Pulsar proxy works, it allows does not expose the Kubernetes node IP addresses and everything outside to the outside world. So, but still the system functions like the way it should be, and allowing to scale the brokers and bookies by using kubectl scale replicas. So it's as easy as to, with one touch of a command, we can scale up bookies, brokers, and proxies. And similarly, if there is a need, the proxies which are exposed to the external nodes can be isolated into a separate system using a node labeling of Kubernetes and isolate from the brokers and bookie nodes, which are highly critical, right? So that's what the segregated deployment means. So then operability. System should continue to online and continue to serve production traffic in several of the maintenance scenarios. And some of the components will be self-adjusting. So for example, bookies should turn themselves into read-only when 90% of the disk is full, and the load manager allows you to balance traffic across the brokers depending upon how much CPU on the broker is being used and or how much memory in the broker is being used. Similarly, disaster recovery scenarios. Of course, critical data from each enterprise flows through Splunk products, and customer exposed expect continuous availability in cloud or on-premise, are required to handle data center failures seamlessly. And Pulsar provides both a synchronous replication and asynchronous replication. You can emulate a disaster recovery scenarios by having multiple Pulsar cluster across different regions or across different data centers, and then the producer produces in one of the data center, and the data is asynchronously replicated into the other cluster, and the data is kept around there, and you can restart those producers and consumers when the other data center fails. There's a notion of a replicated subscription which allows you to start the consumers from where it closely left off in the primary data center. And if you really want exactly one kind of scenarios for then we encourage sync replication, that is a stretch cluster. So that stretch cluster can provide exactly one semantics. Then the requirement 13, performance and total cost of ownership. Splunk applications are widely varied from a real timing requirement. Sometimes the real time is a necessity, which is less than 10 milliseconds, and there are near real time, which is less than few minutes, and sometimes the application requires high throughput in terms of ability to handle multi-petabyte day in a single cluster. And we did compare with a detailed performance study with Kafka, And some of the performance experiments are, and the results are as follows. These are the settings that we used. We used AWS i3 8x large machines with 32 CPU each and 244 GB of RAM, and 4 NVMe disks and 10 Gbps full duplex, and a dedicated 7 Gbps to the EBS volumes, and 20 large 8x large instances were used, and one tainted group for about 15 instances for running Pulsar versus Kafka, depending upon the experiments that we run. And another tainted group is used for consuming traffic. And we used some of the settings like message sizes of 1K each and the batch sizes of 128K, and time for batching in the sense like 1 millisecond and publish it. So this is we use the standard open source benchmark where we producers are produced into the messaging system and consumers are consumed, and the benchmark coordinator coordinates everything and captures the results. So we fix the throughput and we measure the latency and the resources required. So in the case of 1 gigabyte in and 1 gigabytes out, the Pulsar EBS with journal, which is with persistent durability. Pulsar EBS with no journal means it essentially like means without any F-sync, which means like we replicated durability. And the Pulsar NVMe with the journal means with local disk, not the EBS. And the Kafka is the EBS only because Kafka does not provide F-sync capabilities. Even if it provides, it's more of a background F-sync, which does not provide the replicated durability that, the persistent durability that I talked about. So as you can see, the Pulsar is consistently lower, varies between 5 to 140x in terms of published latency. And similarly, in the case of 1 gigabyte in, 3 gigabyte out, again, the latency is 5 to 150x. And again, 3 gigabytes, 3 gigabytes out, again, the variation in latency is pretty consistent across the board. Then essentially one of the summaries, Pulsar provide consistency lower latency when you publish data. And the number of brokers and bookies used for 1 gigabytes and 1 gigabytes out. Pulsar EBS use with journal requires a little bit of more 13 nodes. That is because of the dual writes, because we write in F-sync into the journal as well as get the data into another disk on the same node, because of the fact that data goes into a separate path and the journal goes into a separate path. So which means essentially we are doing dual writes. So that's why it guarantees persistent durability, so that even if the entire cluster is down, you don't lose data at all. So for that extra durability, you pay some cost for it. On the other hand, with if you're doing replicated durability, our cost is much cheaper. So it is essentially like 20 to 40% less brokers and bookies combination than Kafka compared to the EBS and the NVMe on the Kafka side of things. With the additional 30% more brokers and bookies, you can do persistent durability. This again, the same cases with respect to 1 Gbps and the Gbps out. Then the disk write bandwidth. So Pulsar essentially provides a lot of bandwidth. It exploits a lot of available bandwidth per VM when it essentially writes into the disks. So if we use NVMe, we can get up to 850 megabytes per second. Whereas if we use EBS, because of the fact EBS is provisioned based on the number of IOPS we get, we can get as much as 530. Whereas with journal, we do 250 because it's got the dual writes, because the EBS data path is saturated because that network bandwidth has to split between dual writes. So that's why you get half the bandwidth on that. But Kafka is producing only 350 compared to Pulsar. Again, the same observations. So Pulsar uses 20 to 30% less brokers and bookies since it exploits available disk bandwidth very efficiently. And we have some more additional performance improvements coming as well. So from a CPU usage point of view, the amount of codes that is consumed is much lower, 40 to 60% less codes than Kafka. Kafka uses more CPU due to CRC overhead computation and Scala overhead that we saw. Again, it's the same with respect to 3 Gbps out as well. NIC usage is more or less the same because for when you do multiple replicas on both systems, the system and the publisher has to go into multiple, go via network, not to publish to other brokers. So, which is perfectly. So Pulsar uses 50 to 60% less CPU cores with complete control of memory. So then the number of VMs needed. So Pulsar uses 30 to 60% less VMs than Kafka. This is due to the effective use of the bandwidth per VM by Pulsar. And that happens in both the cases of 1 gigabyte in, 1 gigabyte out, and 1 gigabyte in and 3 gigabytes out. And the number of VMs needed in Pulsar is, as you can see, is much lower compared to this. So essentially, the summary here is Pulsar uses 25 to 50% less VMs for the given throughput. With additional 30% more VMs, Pulsar can support extra durability, which is if we need it. So single partition throughput. One of the key thing is how much, whenever a topic is divided into partitions, how much throughput we can get out of a single partition. So Pulsar actually provides much more higher throughput. It's not limited by the disk bandwidth, whereas because of the underlying architecture in Kafka, where each partition is slotted into a disk, you are limited by the bandwidth of the disk. Whereas in Pulsar, you are not limited not by the bandwidth of the disk. Instead, you can have several disks based on striping and other things that we can do at the storage level. You can even get a higher throughput. So single partition latency, as he said, like the latency is consistently 5x to 100x in terms of even single partition, as we saw earlier in the earlier experiments. So the summary, it's Pulsar is 1.5x to 2x lower in capex cost with 5 to 50x improvement in latency and 2 to 3x lower in opex due to the layered architecture. So this is again the summary of the performance, whatever we did. So the next requirement is observability. So when in production, we need visibility into how the system works, and you need to know the overall health of the system. And the system should expose relevant and detailed metrics, should be allowed to easy to troubleshoot. So Pulsar provides pre-packaged dashboards in terms of system overview metrics, messaging metrics, topic metrics, broker metrics, bookie metrics, proxy metrics, and JVM log metrics. The slew of metrics are available that allows you to troubleshoot the system very quickly. So the ecosystem, Pulsar ecosystem is growing pretty fast in terms of the number of components and integrations are being added. I came to know that a company that is a financial company that is going to adopt Pulsar is going to do around 3,000 integrations. And adoption is over 600 plus companies, then still it's growing at a faster pace. And we are proud to say we are one of the adopters. And we also commit bug fixes and features and everything back into open source because it's in our interest to grow the project. So we are investing a lot in Pulsar. So community also is pretty good. And so we have 320 contributors last that I saw, and 6.7K GitHub stars. We have around 600 plus companies that adopted Pulsar, and we have 30 full-time committers contributing to the project from different companies. And the cool thing in Apache Pulsar project is everything is Apache licensed and it's not vendor controlled. So that allows for a lot of features that is available in Pulsar project can be consumed without the fear of the license being changed later and other things based on because of its vendor control. So that way, it's a pure Apache license based project. And so if you want more details about Apache Web Pulsar versus Apache Kafka, here are some of those features. So there's tons of them. So how we use, now let me come to the highlights of the talk, how we use Pulsar at Splunk. So Pulsar is running as a service in the cloud for processing several billions of messages and consumed by several teams. And Pulsar is integrated into one of the flagship product called the Splunk DSP, which is a stream processing offering from Splunk. That is a core stream product. And from 1.1.0 onwards, it is running with Pulsar. Currently, we have released 1.2 by end of October. And Apache Pulsar is being introduced in several other initiatives as well, which we talk about it as the products become available. Splunk DSP, what does Splunk DSP do? Splunk DSP is a real-time processing solution that collects, processes, and delivers data to Splunk and other destinations in milliseconds. In other words, it allows you to collect data from myriad of sources and filter them, enhance them, normalize them. You can transform the data, then aggregate, format the data, and mask sensitive data, detect patterns and conditions, and turn this raw data into high value information, and protect any sensitive data, and distribute data to Splunk or other destinations, depending upon how the data should be routed. And so if you look at the DSP architecture, we support multiple protocols for data ingestion, the Splunk's HTTP event collector protocol, and Splunk to Splunk protocol, and even the data sources could be batch oriented as well, where the data is periodically collected and sent into a streaming fashion. And once the data is collected, the first thing that hits is the Pulsar. So Pulsar is completely used by the acts as a way to capture the data, and then the stream processing engine picks up the data from a Pulsar and processes the data and sends it to the Splunk index or any other external systems. So Pulsar is at the core. Now Pulsar's footprint is increasing within DSP itself. All the connector framework and all the various things for batch and the streaming connectors where the data is being written out from the DSP is all going to be in Pulsar. So closing remarks, Splunk is committed to advancing Pulsar as it is used by our core products and cloud services. So a lot of current work is going on, and we have improved the Go client in Pulsar based on some of the issues that we reported within the teams used by the teams in Splunk. And we added the support for batch connectors, and we added a Pulsar Kubernetes operator, and we have got critical bug fixes done based on running production at a high scale. And some of them has been already propagated back into upstreamed into the open source, and we are in the process of committing some of the stuff back into open source as well. And the feature work, we are going to take up auto partitioning, where topics need not be associated with any partitions. Instead, the partitions will be a hidden concept where you just create the topic. Depending upon the load, it will automatically adjust itself. Then we are going to enhance the data store, the metadata store, so that you can plug in any metadata store that you want, so that it can coexist with other environments within an enterprise. Then we are going to enhance the state store, which allows you to store state when you're processing in the functions, in the what you call the Pulsar functions or Pulsar connectors, which needs a state in order to cut over from when you cut over because of failure from one function to another function, the state could be retrieved. So we have a booth for a demo of DSP if you're interested, and we are hiring heavily. If you're interested in working Pulsar or in DSP, please visit our booth and talk to some of our folks. Thank you.